As far as the topics today, obviously I want to say a little bit more about why I picked this topic and what I would hope to achieve in the course of our time together today. And then, as with anything, I think it's generally a good idea to jump into terminology a little bit, right? So that we're all talking apples to apples and understanding the same thing. And then the main thrust of what I wanted to do was just to give some context around the kind of data that we might get when we do IHC tests. And more importantly, what's the best way to go about choosing a statistical test to evaluate the data? And I've tried to have relevant examples that we can draw on as we go through the course of our discussions here. So as far as the goal, I hope no one thought that by tuning in today, you'd come out of this with a degree in statistics, because it's a pretty big topic, right? And clearly in one session, we're not going to provide a foundation in the field. But what I was hoping to do is to, by way of sort of an overview, illustrate some scenarios in which those of us in this field, right, may need to apply a statistical test. And then again, given the context of the time we have here, it would be counterproductive to try to drill down into theory too much. But I wanted to focus on Excel and show how to execute some of these tests in Excel. Obviously choosing Excel because everyone has it. Not everyone has some of the other statistical software that are out there. But I will make mention and reference to some other softwares, I think at least a couple of times as we go through this. Yeah, onto the terminology. First and foremost, when we talk about statistics, what does that mean? If you've been through any sort of coursework or other seminars types of things, workshops where there was discussion of statistics, you're probably familiar with these two terms. Descriptive versus inferential statistics. And I think the definitions there are pretty clear on what those are, especially for descriptive. It's just how are we describing the data that we've collected in our experiment, right? Ways of graphing the data, ways of describing them numerically. Certainly the arithmetic average of some data is a descriptive statistic. Standard deviation, the median, the mode, the maximum, minimum value, all of those are examples of descriptive statistics, and they give us a way to describe, again, the data that we've collected. In contrast, inferential statistics is all about drawing conclusions and making decisions, okay? We want to say something about this particular setting, right? What are we evaluating? Is our IHC stain being applied to lung cancer specimens that are collected in the lab? Well, we want to be able to draw some conclusions about how this test functions on the entire population of lung cancer specimens by analyzing samples of lung cancer and then again drawing conclusions about it. So we're inferring things about the population based on the data that we get. So that's kind of the main difference there. And again, I noted that the emphasis for today was about choosing the right statistical test. So we're focusing primarily on the inferential side of things. Continuing with the terms, we just used population and sample, so good idea to define those a little bit. And the population is the entity in which we have interest, right? It's the global collection of objects or individuals or events. What is it we're trying to analyze? And you can talk about infinite or finite populations, but the one thing that the population has in common, whether it's infinite or finite, is why we have to talk about a sample. And that is, it's going to be exceedingly challenging, or if not downright impossible, to evaluate the entire population. So we take a sample, and that's a subset of the population, and that's what we test. That's what gives us our data. And that forms the basis of our statistical test. So we analyze the sample to make inferences about the population. There's a lot of guidances and guidelines about how you select a sample. The absolute most important factor there is it's got to be random. You have to do everything you possibly can to make sure that you're not bringing bias into the study by only choosing samples with certain attributes and so forth. So variable. That's the same as what you probably learned in your algebra class way back in the day, and it's you can read the definition there yourself, but it's a placeholder for something that's going to have a discrete value, right? In algebra, it was the x and the y, right? And x could have any number of different values depending on the scenario, and that's the same thing here. So a variable We could have all kinds of different sorts of variables here, whether it's the temperature we're looking at, the intensity of our stain, any of those things, right? Those are the variables that we're looking at. Continuing on with variables, these first two are also an extension of what you learned in your algebra class, the idea of independent versus dependent variables. And for us in our experiments, independent variables are the things that define how we set our experiment up. What temperatures are we using? What incubation times are we using? Do we have different reagent concentrations? Are we looking at different specimen types? All of those sorts of things are we call them independent because they're the input to our experiment. They're defining how we set it up. In contrast, the dependent variable are the things that we're measuring as a function of our experiment. It's the output. What do we want to get out of this? And obviously for IHC, it's in some way, shape, or form going to be the scores that are generated when those slides are read. So that's in most cases our dependent variable in our world. A few more discriminations we need to make when it comes down to the idea of variables. First is a broad division of qualitative versus quantitative. And I think these names are also fairly explicative for what we're talking about. Qualitative is really just more about an attribute, okay? And if you do in a math class or in a statistics class, right, when they talk about this, the most frequent example that I've ever seen used is eye color, right? A qualitative variable. If you're analyzing people, right, and one of the things you want to look at is eye color, right? That's a qualitative variable. Green versus blue versus red. There's no, I mean, yeah. Okay. In terms of our world, types of qualitative variables might be on the independent side. Maybe we're looking at different clones of an antibody, okay, or comparing different staining instruments, right? Sakura certainly has a staining instrument. Other companies have staining instruments. Maybe you're making a comparison between those, right? So that's another qualitative variable on the input side. On the output side, you know, perhaps ultimately the way you score these slides is just saying they're positive or negative for a marker, okay? That would be considered a qualitative variable on the output side or the dependent side. When we do tests for these types of variables, there's going to be some sort of ranking or other types of comparison going on, and you want to be careful. You don't do incorrect arithmetic operations on these types of data. And on the next slide, we'll make reference to sort of a classical IHC scheme that assigns 0, 1, plus 2, plus, or 3 plus scores. You really ought not to be computing averages on those numbers because those are not the second type, which is the quantitative variable. All right, and we've got another slide that'll talk more about this. Quantitative is what you're more used to thinking of when we talk about numeric data. And you can do all of the arithmetic operations on those types of data. In our IHC world, in the lab, incubation times would be a quantitative variable. Incubation temperatures, right? Because those can be measured in numbers, and those numbers have meaning with relation to each other. Different concentrations of reagent, right? On the output side, a dependent variable that we would have that we might consider quantitative would be perhaps we're counting cells and finding out what percentage of those cells are actually positive for a marker, those sorts of things. So these have meaning in our world, so we need to understand that. One more level of division here is on the variable side. It's important because this has direct impact on how you choose to analyze your data. Depending on the textbook that you look at, you can find a lot of different variations on this scheme. You can find some subcategorizations within these different elements. And you can actually find a few that might sort of contradict each other, but hey, that's life, right? That's different authors writing different books. But I think an overall commonality that you're going to see are these three here, and I think these will get you, 95% of the time. These will help you understand what you have and direct you towards the proper statistical test. And that is nominal, ordinal, and continuous. And so nominal and ordinal are types of qualitative, whereas the continuous is our primary form of quantitative that we're going to see. So in terms of what's the difference between nominal and ordinal, the eye color, that's a typical nominal or categorical variable. In our IHC world, positive, negative status, pass, fail, acceptable, not acceptable, that types of things. If you're evaluating the quality of a stain, right? Is it acceptable, not acceptable? That's a categorical output there. Ordinal incorporates this idea of ranking, ordered position, and that's where we get to this 0, 1 plus 2 plus 3 plus scale. Okay, the order of those has meaning. 1 means there's more of something than 0. 2 means there's more of something than 1, and so forth. But what we can't say with this is that the difference between 1 and 0 is the same as the difference between 2 and 1, or the same as the difference between 3 and 2. We cannot say that, okay? And you really want to be cautious about evaluating that type of data in that manner. You can find yourself walking down an incorrect path and drawing an incorrect conclusion if you do that. But the ranking of those has meaning, and so our statistical test will be based on ranking of the data as opposed to calculating means and those sorts of things. And then finally, the continuous variable is indeed a quantitative variable. By the most correct definition, we would say it has an uncountable number of values, right? You just consider the number line. If I say 1 and 2, you can say, well, there's 1.5 in between. And then you can say between 1.5 and 1, there's another value, 1.25, right? And so forth and so on. Any two values I give you, you can find one in between, right? So it's an infinite number of actual values. That's sort of the classical continuous variable. And to contrast this with the ordinal, the differences between numbers have meaning beyond just their order. So now, if we have a continuous variable, the difference between 1 and 0 is the same as the difference between 2 and 1, and it is the same as the difference between 3 and 2, and so forth. Those increments are the same as we move along that scale. So that's the difference there. We can actually consider integer scales as continuous, providing they have more than a few possible values to them. And so that's why I referenced computing percentage of cells positive for a marker as a continuous variable. If you're sitting there actually counting cells on a slide and writing down that you saw 27 negative cells and 45 positive cells, right, then you can calculate a percentage out of that. So you don't have infinite possibilities necessarily there, but you can still consider it as a continuous variable in most cases. So I hope that's clear. And this may it probably sounds like I'm being a little bit pedantic here, but these are fundamentally important in terms of choosing the proper test. You can understand up one side and down the other how to run a test, but if you pick the wrong test, you've made a grievous mistake. So this fundamental stuff is very important. And to again, this idea of selecting our test. How do we do that? It is critical that you choose the appropriate method if you want to have a meaningful value. And so the criteria that drive us to making the choice are some of these things we've just talked about, right? There's a reason I was harping on the type of data, continuous, ordinal, or categorical, that directly guides you to one test versus another. And within your world of continuous data, whether you have what's called normally distributed data or not, we have a follow-up slide on that. How many experimental groups that you have? Do you have 1 or 2 or 3 or more? And I realized too late that I probably should have put greater than or equal to 3 in terms of 3+, but that's not a 3+ IHC score there. How many groups do we have in our experiment? And how many factors do we have? That's slightly different from experimental groups. How many independent variables do we have? Are we only comparing different temperatures? Or are we looking at both temperature variations and concentration variations in our experiment, right? So those are factors. Are we only looking at 1? Are we looking at 2? So forth and so on. So those are two different things, and they both feed into how we choose our test. Also, what type of inference are we looking to make, right? We said for inferential statistics, we're trying to draw a conclusion out of our data. What are we trying to do? Well, the two broadest types of inferences that we can make, on one hand, if we have two groups in our experiment, right, is there a difference between them, or are they the same? Okay, we could just as easily have two groups that we're comparing, and we're not necessarily considering differences, but we want to know, is there some association between them? You got to know what you're doing in order to pick the right test. And then finally, there's this idea of relatedness among your experimental groups. Are they independent or dependent? So the next couple 2-3 slides are going to touch on these in a little bit greater detail. Normally distributed data. This in and of itself is a good hour or 2-hour lecture just to go through what all this means. How do you test for it? And so I would just refer you to other sources if you really needed to do that. But the one kind of nice rule of thumb that we have here, and most sources that you would want to look at are going to agree on this, that if we have, if we are looking at a continuous variable, if our sample size is 30 or more, we can in most cases be safe, assuming that these continuous data are okay to be used and are okay to approximate a normal distribution. And again, what is a normal distribution? Some of you are familiar with that, some of you are not. It's beyond the scope of today to talk about. I just want to introduce this because as you're looking at these things in a textbook or online or something, you're going to see this idea of, are your data normally distributed or not? So that is a decision point that you need to look at. But again, if you have large enough experiments with enough samples, you can generally assume that you're okay in this regard. Two more terms that are important. Methods that are based on having normally distributed data, we call them parametric. Methods that do not require that are called non-parametric. Okay, so oftentimes as you read through some source material that's guiding you towards a particular statistical test, they're going to group them by parametric methods versus non-parametric. And that's what that means. If they're calling it parametric, it has this underlying assumption that your data are normal. Okay. Difference versus association. Maybe just a couple cartoons here would be good for that. On the left is the idea of difference. Okay, so our dependent variable is along the y-axis here. This is the thing we're measuring, right? Whether it's the percentage of cells positive or whatever it is. And then we have sample group A and sample group B. And our data points fall on the graph like this. And that's our question, is do we have evidence to say that B is different from A in terms of these values on the y-axis? That's difference. Association, that you look at the data in a different way, okay? Is there an association? Well, graphically, when you're looking for this, you're going to plot out the independent or the dependent variable for sample A along one axis, the dependent variable for sample B along the other axis, and then you see how they fall out. And if they're just a random cloud, it's probably no association. But if you start to see some sort of pattern there, like we see here, then maybe there is an association. But that's a fundamental difference in the type of analysis you do. And so you really need to understand the goal of your experiment. What are you trying to show? Because that's important in what you do. Relatedness, that was another thing we brought up. This is really mostly a consideration for tests of difference, right? And the reason I say that is hopefully will become clear as we go through these definitions. But any situation where we think we might have association, we're making an underlying assumption of relatedness there. So this really just comes down to test of difference. And do we have independent or dependent samples? Please do not confuse this with the idea of independent versus dependent variable. That's a completely different thing. Okay, it's just sort of an unfortunate that the terminology uses the same words. But independence with regard to your experimental groups says that the specimens are basically randomly assigned to groups, or in other words, the specimens in one group are not related to the specimens in another group. Okay, so the example that we could look at, again, I brought this idea up a little bit earlier of, okay, we want to look at our assay in lung cancer cases, right? And we want to actually look at them across two different laboratories, okay? And so one laboratory is going to stain their own specimens, another laboratory is going to stain their own specimens, and there's no relatedness between the specimens in the two laboratories other than the fact that they're lung cancer specimens. And then we can contrast that to the dependence side of things, where we do have the measuring one sample is related to measuring another sample. And there's a lot of ways you could see this if you look at clinical studies and scientific studies. For us, in terms of IHC intensities, almost always the idea is going to be that we have sort of these paired tissue sections subjected to two versions of an assay. I think probably 80% of the time, if you're looking at a dependent setting in the lab, that's what's going on, okay? Maybe you're looking at two different versions of an assay, whatever that may be, and you choose to cut sections from each block and have a section from every block analyzed by both methods. So there's a clear relatedness there. So you got to choose the right test based on whether your data are dependent or independent. All right, so that's enough on the background terminology. Just one or two more concepts, and we'll start talking about choosing a test. But what is a statistical test anyway, right? Well, it's a way to bring some objectivity to this evaluation of when we think we have an observed effect. And what effects could those be? Well, in our world, we just talked about, right? There's typically going to be either a difference between two sample groups or a correlation, an association between the variables that we're measuring, right? Those are the most frequent scenarios that we're going to be in, right? So if we see an effect, right, we do our experiment and we see that the mean values between our two samples are not numerically the same, right? Does that difference actually have any meaning, right? That's what the statistical test is doing, looking at the values and saying, is that effect that we observed in the data, is it just due to randomness, right, associated with how we set up the experiment? Again, we talked about we sample from a population, and we want it to be random sampling, but even in the random sample process, we're going to get some variation in the way. And we need to understand if the effect we observed is due to the randomness, or is it really present in the population? This phrase here is really the key, right? Are we just, when we saw a slight difference in the calculated mean between the two groups, are we the victim of random variation, or do we really have a difference going on? And if this test tells us that we have a difference, that's when we describe it as statistically significant effect, right? So if you've been reading study reports and journal articles and so forth, and they say they had a statistically significant effect, that's what happened. They ran through this statistical test. They set it up along the guidelines that we just described. They ran it and they saw what result they got, and that's how they describe it. Now, when you look at those studies, you're not always going to see these terminologies here, null and alternative hypotheses, spelled out, but it's an underlying theme to any time that you're applying a statistical test. And I would really encourage you, when you do these sorts of things, to always think in these regards: null hypothesis versus alternative hypothesis, because this really underpins how the test is set up, and it's an important concept to the entire foundation of it, really. The null hypothesis is the effect we seek is actually not present in the population. And certainly then the alternative hypothesis is the opposite of that. The effect we seek is present in the population. So pretty easy to state, right? So that's what guides everything. And then we do our statistical tests, and they're always based on this idea of probabilities, okay? What's the probability of a certain thing occurring? And so ultimately, the output of our statistical test is going to be a calculated probability. We can get other metrics out of it. You all probably heard of the t-statistic or a correlation coefficient or something like that, right? That's an output of a statistical test. But ultimately, the probability value that we get out is the most important thing for drawing our conclusion, and that's what's known as a p-value, p being short for probability. Now, I think everybody's probably aware of this number, this 0.05. If we get a p-value of less than 0.05, we then can reject the null hypothesis in favor of the alternative hypothesis, and we conclude that our effect is present, and that's when we can say our test had statistical significance to it. However, if the p-value is 0.05 or higher, we cannot reject the null hypothesis. We have to accept it, and we conclude that the effect is not there. Now, it doesn't always have to be 0.05. You may come across circumstances where, for whatever reason, the folks running the analysis decided that they needed a lower standard or a higher standard. But I think by far, you're going to see this 0.05 standard put out there. So we've kind of covered the backstory here. Now let's just jump into things. You're going to see in a lot of textbooks something like this table here. Now, what is this? There's a ton of information there. Certainly, I'm not going to read through this to you. This is what we call a sort of a decision tree or a roadmap or a Rosetta Stone to helping you pick the proper statistical test. And like I mentioned with how we categorize different types of data, you can find a lot of these in different textbooks and different resources. They're all going to share the basics. You're going to see some differences. And again, they're going to come down to specific authors' interpretations or personal preferences, but again, they're going to be largely the same as you look at them, certainly for most of the fundamental things. You just want to make sure that you're looking at a reputable source, so a published statistical textbook, for example. And then that gives you the rationale for how you pick it. This here is the citation for this. This is the book that I use on a fair frequency here, and this guidance came about it. And the reason I want to put up here, right, you can see, well, how many samples or groups do you have? How many factors in your experiment do you have? What's your data type? Are we paired or unpaired types of data? Right? Do we have categorical data? So forth and so on. Okay, so all of that stuff we took the time to go through earlier feeds us directly into this. Okay, so hopefully bringing that concept home a little bit better. You really need to take the time to understand your system and use that to guide you to the proper statistical test. Just for today, I just pulled a sort of a subset out of that into these two tables. So if you would refer back to that larger table, you're going to see for tests of difference, there was an area that had this information. So groups 2 or more than 2, factors 1 or more than 1, categorical, ordinal, continuous, and I've slightly modified it based on the way that this author described it. It's couched now in the way we had our prior slide. And you can see if you can identify what you have and the type of data, it'll point you to the right statistical test. And these really are invaluable in terms of keeping you on the correct path. And again, for continuous, we either know we're normally distributed or we have at least 30 samples in our experiment. And then for association, we've just got these ideas here. We're just going to be looking, talking about 2 group comparisons. But again, the data type is important in terms of what we do. And really, we only have a certain amount of time today. So for all practical purposes, I'm just going to touch on the ones that are highlighted in red. But hopefully, by going through this, you get the flavor of what we need to do and how to walk through these things. So let's go ahead and jump right into it. Unpaired t-test. Now, I'm going to stick with this example we put out there before, 2 different laboratories. Let's say our antibody assay is based on Ki67 biomarker. We ask these labs to just take their 50 consecutive breast cancer specimens that they get during the course of their normal work, stain them with our assay, score them, and report back the percent positive scores. And we want to find out if there's any evidence that our assay is performing differently between the 2 laboratories. We're going to use an unpaired t-test, right, because it's pretty obvious here this is not a paired specimen scenario, right? We said they're each analyzing their own specimens. There's no commonality there. But why did we choose t-test? Well, it's percent positive. We've talked about that before. We have 50 specimens, so we're good here. And if we're working with this test, we probably already know that it's normally distributed anyway, but we certainly check that box. We're just comparing 2 sample groups, and it's unpaired. We're looking for a difference. All of those things bring us into the unpaired t-test, right? So all you have to do is look at the scenario, go to your roadmap, and it tells you. So now to execute it, and again, we're going to look at Excel. Excel generally for these things likes you to have your data in separate columns. So lab 1% positive scores, lab 2% positive scores. Again, our null hypothesis says there are no differences between the mean scores in these 2 labs, or our average from lab 1 is equal to our average from lab 2. Again, that's statistically equal, probability type equal. It doesn't mean they have the exact same numerical value. So that's an important concept there. Our alternative hypothesis is exactly the opposite. There is, in fact, a difference between mean scores in the lab. So average from 1 is not equal to average from 2. Put it in columns. You probably have seen these types of things if you've looked in textbooks or different articles. These are all just different names for the unpaired t-test, by the way. So we're going to use this thing called the data analysis tool pack in Excel. I'm sure some of you out there have used it. Maybe some of you have not. You find it in the data tab. All the way over to the right, you'll see data analysis. Now, if you go to look at the computer and it's not there, it means it hasn't been installed. That's not as big a deal as you might think. It's actually part of every Excel installation. It's just not enabled by default. So I'm not going to walk through these. I just cribbed these right out of Excel. So all you need to do is go to Excel help how to do this, and it'll walk you through it. It's really pretty straightforward. You can see analysis tool pack. You just check it and run it, and then it's there. And this link actually takes you to another article about how to install it. So then once you install it, it'll be there to use. And it's really handy because it uses that idea of wizards that Excel likes so much. and I do find them very handy to use. So this is what it looks like. You enable that, it brings you this tool. You can see you've got a menu. You can scroll through, and here we got t-tests and a bunch of different things. We've got some regression, different doodads in here, right? So you would pick the one you want, and you click OK, and it gets you this little wizard, and it's really easy to use. All you have to do is tell it where your data are. So our first variable is in column A. Our second variable is in column B. Where do you want to put that data over the output? I usually just like to keep it in the same worksheet, so I just identify a cell to put it in. Alpha is that standard for significance, right? P equals 0.05 or above or less, right? In Excel, we'll default to 0.05, so don't change that unless you know that you need to change it. And then our hypothesized mean difference, here you should generally leave that as 0 because that's what we're trying to do, right? Where our null hypothesis was there is no difference between our sample groups, so we leave that at 0. You get this all set up, you click OK, and you get this nice output here, t-test. It gives you some descriptive statistics. What were the means between the two labs? Okay, here we saw lab 2 had higher scores. Something called a variance, which I'm sure some of you are familiar with. It basically describes how variable the data are around that mean. Some other things. P is the most important one, and this is the number we're looking for. P, and I'll explain two-tail in a minute. What's the value of that number? Is it less than 0.05? Indeed, in this case, it is. It's 7 times 10 to the minus 5th, so it's way below 0.05. So that says that we have a statistically significant effect. We reject the null hypothesis, and we conclude that indeed we do have differences in those scores between the two labs. Yeah, I don't think I have a separate slide on this idea of one-tailed versus two-tailed, but I'll just say that in almost any circumstance that you're going to do, the two-tailed test is what you're about. Okay, a one-tailed test means you have foreknowledge that one is going to be greater than or less than another. Your average values or something or so forth. And it's really pretty rare that that's something that you've got going on. So unless you know for sure that you should use a one-tail, you should always go with the two-tailed test when you run these things in Excel. So that's really all there is to doing it. Once you know that you need the paired t-test, it's almost trivial to run the test and get the output. So all the important part is getting to that point in Excel and knowing that you have the right test. And that's, again, kind of the information and the concepts that I'm hoping to get across here as we talk today. Now, this idea of variances, I only brought it up because you may have noticed here it said 2 sample assuming equal variances, and that's the one we chose. Can we have unequal variances? Yeah, the shorter answer is yes. That can happen, and Excel does have a test for it. And generally, you don't need to worry about that. It's not a thing you need to worry about too much. There is a test in there. It's called the F test that can tell you if your variances are significantly different. But yeah, in most cases, you don't need to worry about that. Go ahead and do the 2 sample, assuming equal variances. The one caveat I would say is when you get the t-test output, if one of these is twice as big as the other one, then you may worry that you've got something going on, and maybe you go follow through that F test. It's in the wizard as well, so it can be done. But in most cases, the t-test, assuming equal variances, is the one you want. So the paired test, and how would that look? Well, let's stick with our scenario of a P67 assay between 2 different labs, but rather than have them look at their own specimens, what we decided in this case, we are going to provide them with tissue sections. Okay, so from our own repository, we've pulled 50 cases. We've cut 2 sections from each one. We gave 1 set of 50 to lab 1 and 1 set of 50 to lab 2, and then had them do the same thing. They stained them, they scored them, they got the numbers back to us. Now we've got a paired situation because there's very clearly this relatedness between the slides that are stained at each laboratory. All the other circumstances are still there, so we're still with t-test. It's just now we have relatedness and we go with paired. The same basic premises are there, though. The same null and alternative hypotheses, the same arrangement of data in here, okay? So what's different? Well, really the only difference here is we pick t-test paired sample for 2 sample for means. And again, you've done all of the hard work in understanding what your system is and knowing how you fit all of those different definitions for data type and all of that information. That's the hard part, right? Once you get to having the numbers, then it's just a matter of running the actual test. So same wizard, very similar wizard. It's just the underlying calculations are driven by this paired concept, and you get very similar output. In this case, it's a paired 2 sample. Again, we have no foreknowledge that says we need a 1-tailed test, so we stick with 2-tailed test. And again, in this case, we got a significant result. Okay, as you might expect, looking at this, it's those scores are quite different. All right, well, that was the t-test. Another one I wanted to look at is this thing called ANOVA, which stands for Analysis of Variance. Again, this is also for continuous data. We can have unrelated or related. The big difference here is now we're talking about more than 2 groups. For continuous data, 2 groups, we went with t-test. Here we've got continuous data, still only 1 factor, but more than 2 groups. So that's a different test. That's called ANOVA. And again, the decision tree is that if your data fulfill a requirement for a t-test, it automatically fulfills the requirements for performing ANOVA. It needs to be normally distributed or a large enough sample size. It needs to be continuous data, all of those sorts of things. And again, the setup in Excel is very similar. We have a nice wizard. We want to put our data in columns, and then we'll be good to go. Let me introduce a couple terms for ANOVA. These are not new concepts, but they use these terms a little bit differently between t-test and ANOVA. Repeated measures is the same as a paired t-test. So if our groups are related, okay, with the same specimen being represented in each group, okay, they call it repeated measures. I guess the idea of saying paired when we've got 3 or more experimental groups doesn't make a lot of sense. So really, if you have independent data, you don't have repeated measures. If you have dependent data, you do have repeated measures. It's just another way of saying paired data in the context of an ANOVA. So please keep that in mind. Replication is exactly what you think it is in terms of running a scientific experiment. That's the presence of multiple trials within each experimental group. So don't confuse replication with repeated measures there. Hopefully that's a clear concept. Repeated measures, same idea as paired within the t-test. All right, so let's look at ANOVA with no repeated measures. And I'm sticking with this same experimental setup because hopefully it helps us better understand the differences between our t-test situation and our ANOVA situation. So here we brought a 3rd lab into play. Everything else is the same. We've got our T67 assay. We're looking at lung cancer specimens. We're having the labs look at stain their own specimens as they come. But here we've just got 3 labs instead of 2. So how do we do this? Now, the initial reaction that everyone is going to have, if they've not been through these discussions before, is to say, I'm going to compare 1 versus 2, and then I'm going to compare 1 versus 3, and then maybe I'll compare 2 versus 3. Well, in the world of statistics, you do not want to do that, okay? You do not want to do that. You want to do this global ANOVA first and see if there's any difference for any evidence of difference, and then you do your pairwise comparison. So let's go ahead and do that. ANOVA, again, no repeated measures, so we're just picking a basic ANOVA. There's only this single factor, right? It's just the laboratory that we're looking at. So we go into our tool pack, we pick ANOVA single factor. The wizard is, again, very much the same. Here it allows us to just pick all of the input data together as opposed to having to pick individual columns. But it looks exactly the same in general, right? What's our alpha level? Where do we put the output data? Okay, so if we go ahead and do all of this, we get some output. The key thing here is p-value, as you might imagine. Do we have a significant p-value or do we not? And in this case, we did, right? We have evidence that there are differences there. Now, the ANOVA is not going to tell us which lab is different from the others. To do that, now we have to do pairwise comparisons. This is what's called post hoc analysis, right? If you've read any scientific journals or study reports or anything where they talk about doing a post hoc analysis, that's what this means. You have multiple comparisons going on within an experiment. You get a global result, and then you do the individual comparisons to see where those differences are found. With ANOVA, and when you do that, the best post hoc test, the one you're going to find most frequently recommended, is called the Tukey Honest Significant Difference Test. I always thought that was a really bizarre name for a statistical test, but that is the name. Unfortunately, Excel doesn't give us a wizard for that. Okay, it doesn't give us a way to do that. You could, based on very careful reading of the way the test is set up in a textbook, you could do it in Excel, but I really wouldn't recommend trying to do that. I'd say find another piece of software to do it. You know, Excel is not a statistics-based software. It's not. It does give you these things we've looked at. One alternative you can do is there are things called types of add-ins that you can do, and typically they cost a little bit of money, and they'll bring additional statistics functionality to Excel. So that is something that you can look for, and quite possibly some of the labs out there have one of those packages installed. But just for illustration, I'm going to make pairwise comparisons with the t-test here, and you will find some publications that do that. But truth be told, it should be the t-test to do it. But here's where we do our pairwise comparisons: 1 versus 2, 1 versus 3, 2 versus 3. And we've just executed our t-test individually in each case. And what we see is sometimes we get a significant value, sometimes we do not. So this would tell us that 1 versus 2 is significant, 1 versus 3 is not, and 2 versus 3 is significant. So we would probably make the conclusion that 2 is in fact different from the rest. There's something different about 2. You know what, in the interest of time, I'm going to skip this. I think you can access the PDF of this. This is this idea of a family-wise confidence level, family-wise error rate. Have a look at it, but I'm going to skip these slides. I'd rather get through some of the rest of the material. Okay, repeated measures ANOVA. Sticking with our analogy from the t-test, right? We're staying with Q67 scores across our 3 labs, but now we're giving them the slides from the specimen. We cut 3 sections from each of our 50 cases, or 30 or whatever it was, and we gave those to each of the labs, and they stained them. Now we have repeated measures, or paired data in the t-test world, right? This is where we have relatedness. What do? You may have noticed, if you had your eye open for the detail there, the wizard does not have anything for a single factor ANOVA with repeated measures. It doesn't give us that. Now, I don't know if they did this intentionally or not, but as it turns out, if you look at how the underlying tests are done, a 2-factor ANOVA with no replication of data is mathematically the same as a one-way repeated measures. Okay, so you would select that. Again, I'm not going to look at this. These are just a few screen grabs from the web that I put in here. This isn't just me saying that, right? This is something that's been recognized by, and this is the textbook, actually, the one that I referenced before, right? This is widely recognized as being a viable way to do the test. So again, you just go into the tool pack, you pick the right thing, say, okay, you get the wizard, tell it where your data is, where you want the output, and let it rip. Now, since this is a repeated measures, we get a lot more output here, but really it's always this, for ANOVA, it's always this ANOVA table at the end and the p-value that we get. Now, the one thing that's different here is we got 2 p-values instead of just 1. And the reason it's doing that is because this is actually, again, the 2-factor test, so it's giving us 2 p-values. But what you really want to focus on is the columns, right? Because we set up our data in columns, so we only care about the column p-value. And it ends up being significant because it's much less than 0.05, and we would, again, say, yes, we have evidence for difference among the labs. Just like we talked about with the unpaired ANOVA, we would at this point then do pairwise comparison. All right, so I hope that's clear. I know looking at the slides, there's a lot of data there and a lot of information, but really just kind of keep this table in mind. What we really did was to show this one, this one, this one, and this one. And hopefully if you go back to this table and see each of those different scenarios looks like. So what I wanted to do then was just to touch on a couple of these other ones. I've got them highlighted in blue this time because these are things that Excel cannot do, and you need to go somewhere else. But I think it is important to at least look at the type of data that we would have. So what if for our Q67 scores, instead of % positive, we said, you know what, we just are going to evaluate these by a 1, 0, 1 plus 2 plus 3 plus scale. So we cannot use a t-test at this point. This is not continuous data any longer. This is ordinal data. So if you go to your Rosetta Stone, it says you need the Mann-Whitney U-test. You cannot do this in Excel. If our ordinal data were paired, then we need a Wilcoxon sign rank test. The same concepts apply, right? Do you have independent or dependent data? And you have a different test in each case. Can't do this one in Excel. We can extend our ordinal data into the 3-lab scenario. And again, if we have independent data, we get pointed to something called the Kruskal-Wallis test. If we have dependent data, repeated measures, it points us to something called the Friedman's one-way ANOVA. Okay, So why did I bother to show you this? Well, sometimes you're going to be working with this sort of data in your lab, and you've got to know how to evaluate it. We can't do it in Excel easily, so you need another software package. Almost anything you find, Minitab, SPSS, Statistical, there's so many out there. They're all going to enable you to do this, and you may even find some freewares that do that. One that I like, actually, that's very powerful is called R. It's not the most straightforward one to use, but it's a hugely powerful piece of software, and you can do all of these things in it. Again, this is just more for your reference if you ever decided you wanted to get into it. This isn't something you pick up just in a day. I'll caution you that. But if you're kind of into this sort of thing, but if you're into kind of learning an involved new piece of software, and you really want to get into the computing side of things, I really like R, and you can read more about that if you wanted to. Okay, so then just to wrap it up, I got a few more slides where we can talk about tests of association. And this is different from tests of difference, right, as we talked about before. And we'll look at these two, ordinal or continuous data. Sticking with just two groups. So what is association again? Well, it's the opposite of difference, right? It's a different kind of thing. We would set up our null and alternative hypotheses about whether or not there's an association. And our null hypothesis is always there is no association between these variables, and our alternative hypothesis is the opposite, that there is an association. If we get a significant p-value, we reject the null hypothesis, and we have the conclusion that we do have an association. So what would that look like in our world of the lab? Suppose we're developing an assay, and we want to make sure that we've set up our IHC correctly, right? Because everybody knows if you work with IHC, depending on your antibody concentration, your incubation times, so forth and so on, the intensity of the signal, right? The amount of DAB chromogen that you get can vary, and so we want to have the sensitivity of our assay set appropriately. So how do we do that? Well, ideally we have some sort of independent metric. So one of the things you'll find when people set up assays is an independent metric might be looking at the expression of mRNA in some specimens and comparing that to the IHC data. And that'll allow you to set the sensitivity of your IHC assay appropriately. So that's what we have. Here's, in this case, I'm going with HistoScore, which some of you may be familiar with that. If you're not, don't worry about it. It's another type of score that gives us a range of numeric values that we can, by and large, consider to be continuous. And then this column would just be the readout from the I think this was a nanostring actually set of data that I'm showing here, but it's evaluating the amount of mRNA. So we're looking to see if there's an association there. And when you look at it by eye, it does look like it, but we need something objective, right? We need a p-value to come out of this. So if we're going to conclude they are continuous data, we can go with the Pearson correlation coefficient because that's what our roadmap told us. So how do we do it? Well, yeah, the analysis tool pack will help us out. When you look in there, you're going to see two different ones. Now, I know I was calling it correlation, but I'm going to suggest you use the regression function because it's going to give us both the correlation coefficient and the p-value. And really, like I said, we really want to get that p-value. So pick regression. Again, you get a nice wizard. You just tell it where's the data, where do you want the output to be, and it's really pretty easy to do. And it just gives you the output. Now, I've shown two different things with arrows here. One is this, it calls it multiple R. That's the correlation coefficient. And you've probably seen a graph in a presentation before, right, where they gave an R value. And that's what this one is. But we can also get a p-value, all right? And that's shown in the table here. Regression, what's our p-value? And this one is very small again, so we can conclude that we have a significant result there. I said, is that enough? Well, yeah, the p-value is the most important thing. But one of the things you'll notice is people also will make statements about the R value that they get and the size of it. So you can find rules of thumb out there. I provide you with this one, and here's the reference from it. Again, you can find a lot of different rules of thumb that are slightly different, but it basically says how strong of a correlation do you have, and the higher the number, the better your correlation is. So if we have an R value of 0.9 or above, we have a very good correlation. So you always want to report both of them, your correlation and your p-value. Now, one thing here I want to point out is we felt pretty safe that we had normally distributed data, but we made a graph in the context of making a report on our study, we look at it and we're worried, maybe, is this really linear, right? We followed the linear regression model in our tool pack, but look, it starts to bend at the top. So maybe we don't have quite a comfort factor with using the correlation, the Pearsons after all. Well, if you have that concern, then you would go to a non-parametric measure, and the one you would choose is Spearman's rank correlation coefficient. Again, this is something Excel can't do, but we're a little bit lucky here in the sense that Spearman's rank correlation coefficient is Pearson's R calculated on the rank data. Now, what's rank data? It's exactly what it is, right? If you've ever watched a golf tournament, and maybe all of you are making the gag symbol right now, how would I ever watch golf on TV? But if you ever have, right, when they show how people are doing in the tournament, if there's one person at first place and then 3 people tied below him, they give tied ranks to the next one, right? There's multiple people in second place, so we just need to rank our data in that way. And there's a nice function to do it. Rank average is the one you would want to use. And then you convert your raw data into ranked data, okay? And then you just do, again, Pearson's on the ranked data this time. You get the same output. You get, in this case, it's a different number numerically, but we were still significant, and we can conclude that we have a significant association there. Now, if there were ties in the data, if there were a lot of ties in the data, which if you may have noticed as we go through here, there were some ranks that showed up more than once. If you take a moment to look at the PDF, like you probably see number 12 show up more than once in here. I know there are a couple in there. If you have a lot of ranks, you want to use something called Kendall's tau instead of Spearman's. You cannot do that in Excel, so you need to use another software package. One last word on correlation. You can have a value of 0 where there's no association. A value of 1 or -1 means the best correlation. So we can now put more context on our null and alternative hypotheses, right? Our null hypothesis is that there is we say there's no association. What that would mean is that our R value or our rho value for Spearman's or our tau value for Kendall's is equal to 0. If there is an association, we're saying that whichever value that is not equal. And that's really it. And I know there was a ton of information here, and believe me, I struggled a bit in terms of trying to understand how best to present this. But what I really wanted to do is just to give you the flavor of how many different tests are out there, because that can be most likely for most of you. And this was same for me and earlier in my career. What do I do? How do I pick the right test? I'm completely lost when I look at this textbook and I don't know what to do. So that was, for me, the most important thing to get across. And if you're a little bit closer to understanding that concept, then I think I've kind of achieved the goal. As far as actually executing the tests and so forth, hopefully what I showed you in terms of how you do it in Excel was helpful. But for me, it was really, what's the right test to do? How do I understand the path? And once I have the path, then I think I can figure out the rest of it. And that was the goal for today.